Okay, so we stopped looking at this department store problem, and we really didn't look at context for this one much at all whenever we went over it. So I want to go back over this one and look at the context of the problem. So for this, a large department store opens at 9 and closes at 9 p.m. The rate that people enter the store in people per hour is modeled by the function P prime of t, where t is the number of hours since 9 a.m. The table above contains values of P prime of t at selected times. Use the data in the table above to answer the following. And we're supposed to use a left Riemann sum with 3 subintervals, and then I've put this graph here where we can't read it, to find the value of the integral from 0 to 5 of P prime of t dt include units of measure. So P prime of t would be this graph that I have here, and I'm actually just going to make it much larger and cover everything up here so we can see, right? And then on this graph, the x-axis would be our t in hours, and our P prime is here, and it is measured in people per hour. So I've just plotted these points here. So you should have written down the numbers that we used yesterday. But I think it is helpful to think about what this looks like on a graph. So if we're looking at this, we have to use rectangles for the left endpoint. So I want my left endpoint of my rectangle to be on the graph, which the only thing we have are these points here. We could think about trying to draw in a line for this. I mean, we could, let me just do it. I mean, if we just connect the dots here, we've got something like this. Since it's a table, we don't really know for sure what the line would look like because they didn't measure it every second, right? So we would have our first rectangle would look like this. And we can see the width of this, these are counting by 2's here, this would be 2. The width is 2. The height is that first coordinate, that first y coordinate that you had there, which was, what was that? 11, I think, there. And then you have to do the next rectangle. So for the next rectangle, you're connecting this. You're going over to here. You have another width of 2. And then that second dot, that's the height. What number was that for that one? 30. Okay. For our next rectangle, we're looking at this little piece. But see, we have this dot right here. So we're going to have this little skinny rectangle. Not all of our rectangles are going to have the same width. That has a width of 1 and a height of, what's that one? 39? 50. Oh, yeah, I'm looking at it way wrong. 59? 54? I've covered up my table, so it's making it more difficult. The next one would be right here. And that has a width of 1 and a height of, that's 26. I'm getting where I can see my table now. Oh, we were. We did it wrong, didn't we? We're supposed to stop at 5. So 5 would be right here. So we really should not have even done this right here. I did the problem wrong. I think I realized that at the end of class when we were in such a rush that I stopped. So ignore the last dot because our integral is only from 0 to 5 on this one, right? So if we actually calculate that, we've got 22 plus 60 plus 54, which is going to give us 82 plus 54, which is going to give us 136 right there. So our approximation for this is going to be 136. But we need to talk about what that means, right? So since we were looking from 0 to 5, that's our time, right? So from what time is 0 in this case? Because 0 is not like 0 o'clock. It's not midnight, right? It's what time did the store open? 9 a.m. So from 9 a.m. to what would be 5 hours later? 2 p.m. is what we're looking at. That's our time frame. A lot of times you can just do t equals 0 to t equals 5 hours. You could do that here, but it's hours since opening, so this is a better explanation if you're trying to like tell somebody what this really means. So from 9 a.m. to 2 p.m. Now the question is, what is 136? Is it a rate? Is it like sort of an acceleration? Is it the number of people? This is where your units can really come in handy here. Because what we were doing for like when we did 2 times 11, right? 2 was across this side right here, right? That's 2. And that horizontal is being measured in hours, right? So that is, we were doing 2 hours. And then we were multiplying that by this height right here, which was 11. And how is my vertical length being measured here? People per hour. So I've got 2 hours times 11 people per hour. I like to write that as a fraction right there. Well, what's going to happen here is that the hour is like hours over 1. This is all in the numerator, right? Hours cancel with hours here. So I'm just doing this as first rectangle. We really want to look at the whole thing. But I would get 22 people. Just people, right? The hours canceled out. So this is 136 people. So from 9 a.m. to 2 p.m., what has happened in the store? Correct. 136 people enter the store. Okay, questions?
Do we not need to say, like, writing something that
Since it is, yeah, up here for your work, it would be good to say like the integral from 0 to 5 of p prime of t dt and use the squiggle. It would also be better right here if I had used the word approximately. Or about. They're not going to count off for that on this type of Riemann sum problem. Like if your explanation doesn't say approximately, if you kind of word it like it was exactly 136, they won't count off for it, but it's better to say approximately there because you are, Riemann sums don't give us the exact amount there. Okay, 7 asks you to do the right Riemann sum with 4 subintervals from 4 to 5, 5 to 6, 6 to 9, and 9 to 12, still using the same table from above. Okay, so I'm going to do this. I'm going to erase what I had over here. I'm going to reuse that graph. So if we are calculating the right Riemann sum. That means the right end point of our rectangles is going to be on the graph. So like the first interval that we're looking at, they're only asking us to go from 4 to 12. So we don't want to start until we're at 4 right here. And my first interval is from 4 to 5. Right? I want my right endpoint of the graph to be where my rectangle is. What you can kind of think of when you're drawing this up is like, think about like going up both places. I want the right endpoint to be on the graph, which means I got to draw me a line right here. Here's my rectangle. So it's not the tall, skinny rectangle that we had whenever we were looking at the left Riemann sum. It's a little bit shorter, still skinny though. Now, from the table, here's what you're thinking. From 4 to 5, that clearly has a width of 1, so you're going to say the integral from 4 to 12 of p prime of t dt is approximately, we're going to have 1 times, and then I want the right endpoint, which is the y-coordinate of that second coordinate here. That's 26 for that one. So then I need to do the next one, right? So that's from 5 to 6. From 5 to 6, I'm drawing in a rectangle here. I want the right endpoint to be on the graph. So that's going to look like this. If I'm thinking about it here from 5 to 6, that's a width of 1, which I can see on my graph as well. What's the height of this rectangle going to be? It's going to be 21, because this point right here has an x-coordinate of 6, right? So, like this one goes right here, we multiply it by that. Okay? Then on the next piece, I'm going from 6 to 9. That is a distance of 3. So 9 would be right here. So I have a distance right there of 3. And then I want right end point to be on the graph. So I'm going to draw this rectangle right here. So I have 3 times, what's the height of this rectangle? It is 44. And then the last one's weird on the graph, because the last, it's really probably easier to do the last one from the table, because from 9 to 12, that's a distance of 3, and then we multiply that by the height. What is the height? 0. So if we try to draw that on the graph, we don't really have a rectangle for that one, right? Because it goes all the way down to the graph. So once we get all of that, we're just going to calculate. So we got 26 plus 21, and that is going to be 44 times 3 is going to give you 132. And that's going to be 47 plus 132, which is going to give us 5. Oh, I don't know. I put a 5 there. 209. Does that look right? No, that's not right. I'm getting all mixed up and line my stuff up. 179. If it's a free response question, you don't have to give the actual number. But when you're explaining it, it sure does make it a lot easier to talk about it if you have a single number to talk about. So, what do we need to interpret this? What does this tell us? We need to start off talking about our time interval. From 4 to 12, what time would 4 hours be? All right, so from 1 p.m. to what time is 12 hours going to be? 9 p.m. Okay. What happens during this time period? Approximately 179 people enter the store. Okay, questions? Okay, let's look at the last part on this example 8. It says approximate from 0 to 12 using a, oh, I didn't realize I put this on these notes. I didn't read through these well enough. I really don't want to do midpoint just yet. The homework does not have midpoint. We'll do midpoint. We'll do midpoint on the next set of notes whenever we get to it. So ignore 8 for right now. We're not going to do that. So let's flip over and look at the homework that you guys had. And which one is that? This one here. And there was no answer key because I have not done the answer key yet. For that. It is best on this one. Like, I'm just going to go ahead and make this my key. Let me save this as my key. Alright, so it is best when you do these problems, like best practice for this is if they ask you to do a Riemann sum on the free response part of the test, it is best to write the integral from 1 to 8 of f of x dx and then use a squiggly equal sign for that. That's the best thing to do for these problems. If you don't write it, you're probably still going to get credit for it. You just run into a little bit of an issue, like if you, once you have to, like, on this one you don't have to explain, but if you have to talk about it and you haven't labeled it, there's a chance you could mess something up where you don't get the credit that you want. The best looking work is going to have this at the beginning here. So if you are doing a right Riemann sum for this one, right, you are looking at the distance from 1 to 3. That's going to give you the width of the rectangle. That would be 2. Then we're doing a right Riemann sum, so what number do we multiply that by? What? 2. Which is the right number. So then we look from 3 to 4. What's the distance there? 1. And then what number do we multiply that by? 5. So 1 times 5. And then the last one from 4 to 8 is 4. And then we're going to multiply that by 7. Like that. And so for this one, you should get 4 plus 5 plus 28. So 9 plus 28 is going to give you 37. Okay, Everybody okay there? Good. All right, so for the second part, you're doing a very similar problem. You're still going to say the integral from 1 to 8 of f of x dx, and you're going to use the squiggly equal sign right here. You are going to still use the same thing, the 2, the 1, and the 4, right? The width of your rectangles does not change. What does change here? We're going to use the left numbers, right? So instead of using 2 for this first step, now we want to use this one, 6. Here we want to use this one, 2. Here we want to use this one, 5 for that. So I would have 2 times 6 plus 1 times 2 plus 4 times 5. So I got 12 plus 2 plus 20. So 14 plus 20 is going to give me 34 for that. Everybody, does this make sense? Everybody okay here? All right. Now, I told you not really to worry about context so much for 3. But now that we have learned about context, we talked about context a little bit more, we want to add that in right here. So after the basketball game, the rate that fans exit the school is modeled by the function capital L, where capital L is measured in fans per second, and T is measured in seconds. Values of L are given in the table above for selected values of T. Use a left Riemann sum with 3 subintervals indicated in the table above to approximate the total number of fans that exited the school from T equals 0 to T equals 6. So I'm going to write an integral expression for this. We are doing the integral from 0 to 6 of capital L of T dt, and I'm going to use a squiggly equal sign. And they said to use a left Riemann sum here. So you're going to do 2, and then you're going to multiply by the 3.5. Then we will have the distance from 2 to 3 is 1. Multiply that by 2.0. And then from 3 to 6, we have 3. We'll multiply that by 2.1. Okay, so I'm just going to grab the calculator for that here quickly. We've got 15.3. So, this is good. Now we need to explain what's happening here, right? So it helps me to think about what was my T measured in? Seconds. And what was L of T measured in? Fans. Just fans? L is measured in fans per second. There. So, whenever we look at this here, I'm going to be multiplying, like when I multiply that 2 by the 3.5, right? 2 is measured in seconds. 3.5 is measured in fans per second. What happens here with the seconds? They cancel each other out, right? So, what units do I have here? Just fans. And you do have a decimal here, which we can't really have 0.3 of a fan, but you want to keep that decimal. You want to continue to use that decimal because whenever we use analytics like this, sometimes we get decimals. It doesn't mean that we literally have 0.3 of a person walking through, but it does tell us something, right? Because if we start expanding this over time, was it exactly 15? Was it a little less than 15? Was it a little more than 15? It makes a difference. So you want to keep your decimals, even though it technically is going to be a whole person. Now, what is our, what like sentence could we write for this situation?
Do we always need a sentence for this kind of stuff?
You could probably get away with not doing it here based on the way this question is worded. It asks you for a sentence a lot of times, and it wouldn't hurt to put it. Right. A lot of times, the AP stuff will ask you to interpret the context. It doesn't specifically say that here, but let's throw that in and do that here. What's happening? What kind of sentence could we write? Okay, sound good? Beautiful. You can change the order. You can word it a little bit differently, but that's the general idea that you're looking at. Okay, and that last one, you had to write me definite intervals for these. So for the first one here, you should have the interval of g of x dx, and the limits on this should be from -4 to +3. For the second one, you should get the integral of h prime of x dx, and the limits on this one should be -2 to +6. And this last graph's pretty crazy. We haven't really seen one like this yet. It's something that we will need to talk about here in the future. But the graph is v of t, so we would have the integral of v of t dt, and it's just going to be from -3 to 7. You're still just looking at those endpoints. Now, what happens right here is if you have an area that's underneath the x-axis, like these two areas right here, when we integrate them, we get a negative value. And whenever we have areas above the curve, which is really all we looked at yesterday, right? We didn't do anything where we had a graph below, then you're going to get a positive value. So you could actually get like negative answers for these, which in the context of like number of people doesn't make sense, right? But in some context, it could make sense, like temperatures or if you're looking at a rate, it makes sense to have a negative rate in a lot of cases. Okay, we okay here?
So with the value of the table, then it'd be negative 1.
Yes, yes. So like if you were doing like a Riemann sum on the table, you'll get a negative value. And you just go with it. Like you do if you have negative values on the table, you just still do the same process. You say, oh, from here to here is this far, multiply it by the left endpoint. From here to here is this far, multiply by the left endpoint. So if it's the same process, you're just going to get some negative numbers along the way. Okay, questions? Okay, you guys have the back side of this, which is going to ask you to do a couple other things, and these will be in context here. I want you guys to try that now. Also, try to make your work like pretty nice and neat and beautiful, because I am going to take these up also for my national board stuff. It's just participation as far as your grade goes, but this kind of like ties into the activity that we did over here, so I need to take that up. 5 should be, hopefully the mechanics of solving the numbers is not that bad for you. You're doing okay on that. The explanation, I think, is really like the hard part of a lot of these. here, so you should get 312 for this first one. All right, you're just doing 7 times 5, 4 times 23, 5 times 37. It did not ask you for units on number 5, and it did not ask you to interpret number 5 for a very good reason. Because if you'll think about multiplying 7 times 5, 7 is measured in minutes. 5 is measured in people. So when you multiply those together, you get 35 minutes times people, which I do not know how to explain what that would be, right? Like, that's not really units we would ever talk about. Minutes times people. But that would be the units. You don't have to write it down right here. It was not asking for units right here. I wrote it down to help me on number 6. Okay? So number 6 asks for the 1 over 16 times this value. And they didn't tell you anything about units, but we need to think about what that could possibly mean. If we multiply something by 1 over 16, that's the same as just dividing that number by 16, right? So basically we're taking 312 and divided by 16. You should get 19.5, I believe. Does that sound right? The actual, like, getting the number, you just take 1 over 16, you multiply it by 312, you get 19.5. Any ideas on what that means? Good. Kind of, we want to use like one more word to get it right. We definitely are going to have people. The units help me think about it here, so you don't get something like really crazy here. 16 is the number of minutes that we're looking at here. So even though they didn't write it here, you're really thinking of like 1 over 16 minutes. We're dividing by 16 minutes here, right? So if we do that and multiply this by 312, the minutes in the bottom cancel with that weird minutes in the top, and we just get people for this. So we are talking about 19.5 people. So anytime we're doing anything with intervals that have limits on them, we want to give the time period when this is happening. So from t equals 0 to t equals 16, it's minutes on this one, right? Minutes. There is, what's going to happen here is going to be like our average, right? So there is an average of 19.5 people in the store. And we will get to the section where we work on finding average value using intervals. I think it's in Unit 6. It's just a little bit later. But Mr. Passwater's just kind of throwing this in a little bit early to get you kind of thinking about, oh, what could this be? If you just keep those units with it at least sort of helps you know what you're talking about. We're not talking about a rate here because the units are just people, right? We're talking about the number of people in the store. Okay. You could probably, like Molly just said, that there was 19.5 people in the store. You could probably get away with that, because it sort of understood you meant average there. You might could get away with that. Okay, there. All right, for 7, you should get 7 meters per second. It did not specifically ask for units here, but you're definitely going to have them on the second part. And I have drawn in my rectangles that I used here. Notice all of my rectangles, their left end point is on the graph. if they have you do one from a graph, they will give you a graph where you can tell exact grid lines where those should be there. Or they will give you the equation so that you can find it out. But in this case, they were just whole numbers. So we should get 7. We are supposed to look at our integral from 0 to 4. If this is acceleration, which is in meters per second, and we multiply that by seconds, right? We are finding the area under the curve. So we're doing meters per second times seconds. We will get meters per second for our units. So what is our result giving us if the units are in meters per second? Velocity. And specifically, what it's going to be your total change in velocity, right? Because what happens is, like, from here to here, that was that first rectangle was 1 meter per second. So the velocity increased 1 meter per second. If it was like 12, now it's 13. And then the next one is 3. So in that next second, your velocity increased 3 more, right? You don't want to just say the velocity is 7, because you don't know what the velocity was to begin with, right? If the car began from stopped, then the velocity is 7 at the end. But if this car was already going 10 meters per second, then the velocity would be 17 at the end. So it's our change in velocity that we're looking at. So you could say something like this: from t equals 0 to t equals 4, the total change in velocity is 7 meters per second. Okay, questions? Okay, if you guys don't mind, make sure, well, it really doesn't matter if your names are on or not, because I think I have to black them out if I do use them, but put your name on just so I know, because I think I have to use, like, even though they don't know if I use the same student or not. So, one new option that I'm going to throw out there for you is that rather than using rectangles, we could use trapezoids. Okay? If you think about, we've got a picture drawn over here. Think about, if I did a left Riemann sum here, it would look like this. There. All right, that would be what the left Riemann sum would look like. And a left Riemann sum, especially if you're not using that many intervals, gives you a pretty bad approximation sometimes, right? Like, we're not too far off on these first 3, but look at this big gap right here that we have in our graph. That's just not ideal for us here. So, one option that typically is going to give you a better approximation is that you could use a trapezoid instead. Okay, so we did trapezoids the other day when we were finding an area under the curve. I gave you this formula. I also said another option for your trapezoid formula is to do height times base 1 plus base 2 divided by 2, so it's just the height times the average of the bases. You can use either one. It does not matter which one you choose to do here. It's just, make sure you've got it memorized right there. So let's look at what we can do finding a trapezoidal approximation. Okay, so I would like for us to sketch a little graph for this first one. Now, we're going to learn how to do it without sketching a graph, but I think especially at this beginning part. It's just easier if we can see what the trapezoid looks like. So we need our x-axis to go to 14. Y-axis needs to go to at least 11. So okay, and these won't be perfect, but we're going to graph these points here. 2, 5, 8. We've got 10, 4, and then 14, 0. So, especially if you have small numbers, I have a lot of students that graph this every time. It just helps them see what they're doing here. It takes a little longer, but it might be worth it for a right answer if you have time to do it here. Because the trapezoidal rule can get a little bit confusing from the table, right? So this first trapezoid that we would draw in right here would be right here, right? So whenever we look at our trapezoid, the bases have to be the parallel sides. So our trapezoid, our base 1 is right here, our base 2 is right here, and then this side right here, which we really want to call the width because of the way it's oriented, is actually the height. Because in a trapezoid, the bases have to be the parallel sides. The height is the distance between those sides. So in this case, for my first trapezoid, the height is 2. If you're thinking about the table, that comes from here. It's really like your width, right? And then I need the average of the bases, right, for my other piece that needs to be multiplied together here. So base 1 right here, that's going to be 7. And base 2 is going to be 11. So you end up using, both of these, right? Those are your two bases. So you have 7 plus 11 divided by 2. Then you go on to the next trapezoid. If I look at the next trapezoid, I've got this trapezoid here. What's the height of that trapezoid? It really looks kind of like width on the graph. 3. I can find that here, going from 2 to 5. That's a width of 3. And then I use both of these endpoints as my two bases, right? So I'll have 11 plus 8 divided by 2. I'll keep going. My next trapezoid is going to be this big fat one here. What's the height of that trapezoid?
5.
It's going to be 5. And then this base right here is 8. This base right here is 4. So I'll have 5 times 8 plus 4 divided by 2. Now my last one, is it actually a trapezoid? What shape is it really if I draw it in? It's really just a triangle. You can still use trapezoidal formula though. It's going to work the same way. We're going to do a width, or height there of 4. And then we're going to do the two bases 4 plus 0 divided by 2. It ends up being a triangle formula because you're doing the base times the height divided by 2 for that. So it works out even though it's not actually a trapezoid, right? So you don't have to change your process for that. So now you're just simplifying. In this case, here those 2's could cancel. You'll get 18. Here, oh gosh, this one's not as pretty. This one's going to be 3 times 19 over 2. Ugh. This is going to be 8 plus 4 is 12. Divided by 2 will be 6. So that's going to be 5 times 6 right there. And then this is going to be 4 times 2. So we got 18 plus, let's see, 19 times 3 is going to be, let's see, 57 plus 30 plus 8. So 18 and 38 is going to give me 56 plus 57 over 2. And so if I want to put those together, really, we're talking about amusement parks. A fraction's not that helpful here, really, right? I would rather have a decimal in this case because we're talking about in context of an amusement park and number of people and things like that. A decimal would be more helpful. So half of 57 is going to be, let's see, half 50 is 25, then 28.5. And if I add that together, I've got 84.5. Just double check me on my mental math here. Does that sound okay? Yes. No. For the 14, oh, well, okay, hold on. 9 to 7. Ooh, did I go too far again? It is 3 subintervals. Don't do what I've done. Kids do this a lot, though. This is a very common mistake. I automatically went with everything that was in the table. But Lucas is very intelligently pointed out that I was only supposed to be using 3 subintervals. How many did I use? 4. And I was only supposed to go from 9 a.m. to 7 p.m., which is 10 hours. I was supposed to stop right here. I was not supposed to use that last part. So let's cross this out. Let's cross this out. That's just going to take 8 away from our answer. So let's just cross out that. And we're going to just take 8 away here. And we really should have gotten 76.5. Does that sound better? I think for that. I should have been much more careful. They'll do this to, they don't always do this to you on the AP exams. Sometimes you're supposed to use the whole table. A lot of worksheets I've used in the past, you use the whole table. But every once in a while, they only ask you for a piece of the table, and you should not do what I just did. There. So we got 76.5. Now we need to think about what that means, right? Think about your units. You were taking, like your 2 right here. Whenever you multiplied the 2 by the average of the bases, right? 2 was in hours. The 7 and 11 we're both in people per hour. So I'm multiplying hours times people per hour. So 2 right there doesn't really have a unit with it because it's just dividing. The hours cancel, and I just get people. So this is 76.5 people. Okay. We are not told to interpret here because the question, like they didn't specifically say, they give you what it means in the question, right? To estimate the total number of people that entered the park from 9 a.m. to 7 p.m. So we got 76.5. I was a little lazy here and did not do my integral from 0 to 10. If I'd done that, that may have made me think about my time a little more there. P prime of t dt, squiggly equal sign over there. Okay, questions here? He does make a note here. In this previous example, we approximated this. It gave us the total number of people that entered the park from 9 a.m. to 7 p.m. In general, we need to carefully consider whether we have found a total or the net change when interpreting a definite interval. Okay. In this case, we were looking at the number of people that enter the park. We are only looking at the number of people that enter the park. We did not have any negative rates right there, which using negative rates would be telling us people are actually leaving the park, right? A lot of questions you're going to get will give you a separate equation that says, oh, they're leaving the park at this rate. And then you got to consider those two things together. We're not doing that here. So we're only looking at people entering the park. All of our rates are positive. So people are just constantly positively entering the park here, right? So our total amount of people is just increasing the whole time. So this is giving us a total for this. However, if we had some negative values here, if there were people leaving the park, then this would not be the total amount, but would be the net change, the change in the number of people. This is still the net change of people who entered the park. It's just also the total, right? If everything's positive, then the net change and the total equal each other. Think about like your bank account, right? If you keep your bank account in the positives, which is where you want it to be, and you are just looking at the amount of money in the bank account, there, you know, everything's positive. You're talking about total. If you have, like say you have a savings account and you only put money in the savings account, you do not take any money out of it ever. Then the total amount of money in your banking account, in your savings account, is the same as the net change, right? But if you are looking at a savings account, you put money in, you take money out, you put some more in, you take some out, then you could be looking at the total may not match the net change, the total amount that you put in versus net change. So you got to be careful with that. Here we're just working with context on these two questions here, and let's see, we might be able to talk about that a little bit, and then we'll probably have to stop. All right, so for example 2, the amount of money in a bank account is changing at a rate A prime of t, where A is measured in dollars per day and t is the number of days since January 1st. Interpret the following in context. So when we integrate, we're finding an area, right? And on our graph, they're telling us t is the number of days and A prime is dollars per day. I think Oh. I wonder if that is a typo or if he meant to do that. Because he calls this A prime, but then says A is measured in dollars per day, not A prime is measured in dollars per day.
So then A prime will be measured in dollars per day.
Yes. Let's go with what he's got here. I'm not sure. So if A is in dollars per day, then A prime is in dollars per day. Alright, so if we integrate A prime, then we would be finding all these. You can think of it like you're finding an area of a rectangle, even if you're doing the exact value, right? We're multiplying. It is easier here to do dollars per day squared instead of dollars per day, then you don't have a complex fraction, times the number of days. And that, of course, would be over 1. And one of these days cancels with one of the days in the bottom. So our units here are dollars per day. I wonder if this is hard to interpret. I wonder if he meant to put an A prime on that. It would be much easier to interpret if you had put a day on that. So if we're talking about dollars per day, we're not talking about the amount of money in the account. We're talking about the rate at which the money is changing, right? So anytime you do any of these, you need to start off with your time frame. So we're going to say from, in this case, you could say January 1st to January 10th, or I would just do t equals 0 to t equals 10 days here. The A prime, well, dollars per day is going to be the rate that the amount of money changes. So the rate let's just call it the balance. The rate that the balance, that'll be easier to word. The rate that the balance changes. The rate that the balance changes. This is bad wording. Or let's use decreases. $853. Just put my dollars right here per day. I use decreases since I'm getting a negative answer here. And then I did not put the negative with the 853. If he really meant to put a prime right there, then we would just be talking about the total amount change of the account, which would be much easier to think about. He may have meant to put that there, I'm not sure. Okay, let's look at the next one really quick. Rate in dollars per day that Mr. Passwater spends money can be modeled by S of T, where T is number of days and S, they said, is dollars per day. All right, so if we multiply those together, this time we have dollars per day times days, and the days cancel, and I just get dollars, right? So now I can say from t equals 0 to t equals 10 days. So we're just talking about dollars. So what's this telling us about Mr. Passwater and the amount of money he spends? It's not the rate he's spending money anymore. It's how much he spent. So Mr. Passwater spent $2,457.